Good morning, everyone. My name is Jasanch, and today I'm going to present you our demo entitled Live Demonstration of Service Function Chaining Allocation in Fog Computing. These are the demo steps for today, and I'm going to start by making a short introduction on how we can deal with service function chaining concepts in a fog cloud infrastructure. Fog computing essentially is an evolution from the cloud computing paradigm where you try to distribute the resources available in the network by placing them at the network edge. And usually you have three main layers in fog computing: the cloud layer, the fog layer, and the IoT layer. Service function chaining essentially is trying to form an order of individual services that each user will have to traverse the path so that he can access a particular network service. And one of the things that we noticed is that service function chaining concepts are still quite unexplored for fog computing, because most research is focused on Mac use cases and little attention is given to fog computing. So we thought, how could we incorporate service function chaining concepts in a fog cloud infrastructure? We decided to have a practical implementation by using a very well-known container management platform called Kubernetes, where we have built a Raspberry Pi cluster for our NETSOFT 2020 demo, where we have 4 cities as infrastructure locations and 7 Raspberry Pis. And this cluster will be showcased in the next slide. We have here our Raspberry Pi cluster. For instance, on the left side, we have our master node representing Brussels, and then all the 6 worker nodes are representing the other infrastructure locations: Ghent, Antwerp, and Bruges. Our SFC controller has been implemented by extending the default mechanism available in Kubernetes called KS, where we let him apply node filtering as the first step in the scheduling process by filtering out inappropriate nodes at the beginning, and then we make the final decision purely based on latency reduction and bandwidth conservation. And we do this by using a feature already available in Kubernetes called node labels that I will show you later today, that we can map, for instance, the entire infrastructure in these node labels. For instance, using these node labels to set up requirements in terms of bandwidth that each node has in terms of capacity. So now let's see how we can install our SFC controller. You need 2 configuration files. The first one is a policy configuration file where you can define, for instance, the set of predicates that the code scheduler will use to apply node filtering. And then you need to define the extended process so that you can find our SFC controller to make the final decision in terms of allocation. And the other configuration file can be considered as the main configuration file of the SFC controller, where, for instance, you can define the containers that will run in this pod. And before I apply these 2 configuration files to deploy the SFC controller in our infrastructure, let's check a feature that I mentioned in the previous slide about node labels. As you can see, I introduced information about our infrastructure, specifically in terms of bandwidth and latency. And for instance, each worker node has an available capacity of 5.0 megabits per second, while the master node has a capacity of 10 megabits per second. And we will see that our SFC controller will be able to pick up all this information at runtime. So let's apply both configuration files. As you can see, the deployment has been created, so let's see if the pod is already running. The container is still being created. Let's check again. And the container is running. And to check that in fact is operating properly and he was able to collect all information, let's check the logs. And as you can see, the SFC controller started and was able to collect all information that we have placed as node labels. For the evaluation, we have designed a use case based on a waste management system that we foresee in future smart cities. And our service chain has 4 services: an API, a database, a route planner, and a server. And essentially, we have a waste bin sensor that will collect the bin's fill level at a given time and send this data throughout the service chain. In this slide, we have the allocation requirements for each of the individual services that we have in our service chain. And for instance, the main ones are the replication factor, the policy that will be applied by our SFC controller, the target location, if any, and a minimum bandwidth requirement that essentially tells our SFC controller that you need to reserve this amount so that the service can operate properly. And for instance, one of the services, the route planner service, has a target location Brussels, our city Brussels, and the policy specified is location because we want to deploy this service in the cloud because it needs more resources. So now let's deploy our service chain and compare the allocation schemes between the KS and the SFC controller. Here we have the nodes in our infrastructure, we have 7 nodes, and now let's check the pods deployed by the KS. So far we have no pod here because we didn't apply the configuration files for each of the individual service in our service chain. So let's deploy the configuration files where we say to our system to deploy them based on the kube scheduler. So the pods have been created. Let's check if they are running in the system. So almost all of them are running. Let's check again. So they are running. Let's reload this page and you can see here the pods that we just created. And they were allocated by the default scheduler. So let's check results in terms of execution time. And you can see here that the KS took 5.5 seconds allocating all these pods. Now let's do the same procedure for the SFC controller. As you may notice here, we don't have any pod yet. So let's apply the same command, but this time we will tell our system to deploy these pods based on our SFC controller. Pods are being created. Let's check if they are already running in the system. Some of them are running, others are being created. Let's give a bit more seconds. Let's check again. So they are running. Let's reload this page. And you can see here that the pods were allocated and they were based on our SFC controller. So let's check again the results in terms of execution time. And as you may notice, the SFC controller took a bit longer, took 6.6 seconds. And usually we noticed in our experiments that depending on the scale of your test bed, this could be an increase of about 10 to 30% in terms of execution time. Now let's check results in terms of the load of the infrastructure. And you may notice that the allocation scheme of the KS gives us some inefficiencies, let's say. Because, for instance, the worker 5 has an allocated bandwidth of 8.0 megabits and the worker 6 has 7, which is higher than the limitation of 5.0 that we have placed for each of the worker nodes. While the SFC controller was able to allocate all services and stay below the 5.0 for each of the worker nodes. So now let's check results in terms of service latency. And we notice that our SFC controller was able to reduce the average end-to-end latency of the service chain. The KS achieved the results of 46.5 milliseconds, while our SFC controller was able to achieve 35 milliseconds. We noticed also that we can achieve reductions up until 40% while maintaining bandwidth depending on the size of your infrastructure based on the experiments that we have run. So as you notice here, our SFC controller is able to reduce the end-to-end latency in our system while maintaining bandwidth requirements. Let me finish our demo by thank you all for your attention, and let me mention that if you are interested in knowing more about our work, you have here the GitHub repository link that you can access, and please contact us if you have further questions. Thank you.